in a closed circuit. The PD that you are going to read after connecting the resistor is going to be the terminal PD, V. And now we are saying that the terminal PD is usually lower than terminal PD, we call it V prime. Usually, terminal PD is usually less than the EMF. And we are saying, where is the extra voltage going? That extra voltage is used in overcoming the internal resistance, small r, within the cell. And that internal resistance within the cell, once you get the PD across the internal resistance, add it to the terminal PD, you get the EMF of the cell. And that is the reason why we say internal resistance is the opposition to the flow of current within the cell due to its chemical composition. The chemicals within the cell tend to oppose the flow of current through the cell itself. And therefore, the extra PD you use is the PD required to overcome the internal resistance of the cell. And that is the reason why we say that EMF E is equal to terminal PD plus the EMF required to overcome the internal resistance of the cell, which is I small r. Or we can use E equal to V, which is from Ohm's law IR, plus I small r. This is terminal. This is now what we are going to call it, terminal PD. This one is the lost PD, the PD that you waste in overcoming internal resistance. Now, when you factorize out I, you end up having I is equal to R plus R. So this is the expression that relates EMF, internal resistance, and that. But also, from here, you can now say that from here, you can find that R is equal to E minus V over I. So if you want to get internal resistance, you can get the EMF, subtract off the terminal PD, divided by current, you get the internal resistance small r. That is what we had in our previous lesson in the summary. Now let's handle issues of activity 1, which I suppose you tried. So activity 1, remember there are 2 activities. Activity 1, there was a circuit drawn like this, where there is a voltmeter across, and then there is an ammeter, a resistor, and a switch. So the diagram was like that. All right. So the question was, when switch K, do you all see switch K? The diagram. So when switch K is closed, according to the question that you have, note it clearly from the diagram. The question is saying when switch K is open, the reading of the voltmeter is 1.4 volts. When K is open, the reading of the voltmeter is 1.4 volts. When switch K is closed, the ammeter reading is 1.0 volts. The ammeter reading is 1.0 amperes, and the voltmeter reading is 0.9 volts. I'm beginning with Kathy. Write an expression relating E, ammeter, voltmeter, reading V, and the internal resistance R. Yes, what is the expression? We answered in Roman 1 of the question. Yes. What is the expression relating EMF E, ammeter reading I, voltmeter reading V, and internal resistance R of the cell? Yes. Feel free. The answer is already here. So the expression is A equal to I plus R. That is the only answer we wanted. Roman 2. Calculate the internal resistance of the cell. Calculate the internal resistance of the cell. What are you going to use to calculate the internal resistance of the cell? Yes, feel free. How can you get the internal resistance of the cell? Internal resistance of the cell. R equal to E minus V over I. So we could now see E was, what is E now, by the way? Was E given? Was it given? And how did you know that it is the one? Yes. Numbers faster. Yes, we defined EMF E as the terminal PD in an open circuit. You could say we have our voltmeter at this point. These points are terminals of this battery. Are you getting it? Terminal here is attached here, and the terminal here is attached here. So if it is open circuit, it implies that this is now going to read EMF. And according to our question, it was reading 1.4 volts. So that means EMF is 1.4 volts. And when we closed the circuit, the voltmeter was reading 0.9, meaning that the terminal PD is 0.9 over the current I, which was 1 ampere. And therefore the internal resistance turns out to be 0.5 ohms. Did you find challenges in that one? The only thing I know, you could not find any challenge unless you did not decide to do the work. But if you committed yourself, it was straightforward from the question, from the notes. Then find the value of resistance R. Find the value of resistance R here. So, according to what we have, how can we get the value of resistance R? How can we get R? We know everything except R. We know I, we know E, we have volts. Small r we can, yes. So you can now get it from E equal to I into R plus R is 1.4, current I is 1.0, R plus 0.5. See that? So therefore, R is now going to be equal to, and this is 1 as if it is nothing. It's going to be R minus 1.4. So 1.4 minus 0.5 gives you 1.4 minus 0.5. 0.9 ohms. So hoping that one you have found it very convenient and easy. Number 1 is done. Number 2. We are all these questions are connected with internal resistance and terminal PD. Do you see question 2? Question 2 of activity 1 is saying, explain why 8 cells arranged in series cannot be used to start a car while a battery of the same EMF can. What explanation are you offering? We are saying 8 cells connected in series cannot be used to start a car. And you would bring your car and then add the cells and then it works. But a battery of the same EMF can. What do you think is the reason? Why do you think the cells cannot, but the battery can? It's a group of cells. But the cells, once you make those group of cells, cannot start a battery. You connect it to the topic we are handling. You see, when you get cells and you connect them in series, even the internal resistance increases. Do you know that? Yes, when you get cells and connect them in series, each of the cells has an internal resistance. So when you connect them in series, you are going to realize that the effective internal resistance is going to be R1 plus R2 plus R3 plus R4. So the internal resistance is going to increase. Are you getting me? Yes. So that means the effective EMF, the current they are going to get. Because if you remember, you see the expression here. You make I the subject of the formula, you're going to realize that E is equal to over R. That means if the internal resistance increases, are you getting it? Current decreases because you are dividing by a numerator. Are you getting it? Yes. So when you make cells in series, you are increasing internal resistance. And therefore, the current is reducing. And it's the current that drives the engine. Are you getting it? So the best answer would be is that the cells will have very high internal resistance. The cells will have a very high internal resistance. Internal resistance. Compared to the battery. And if they have a very high internal resistance compared to the battery, hence very little current will be drawn from them. Hence, very little current will be drawn from them. Very little current will be drawn from them. We are going to release very little current, even if the voltage is big. Because that big voltage means the constants have been reduced by by the increase in internal resistance. I'm getting it. The internal resistance is going to consume most of the current, and therefore the energy required to start the car will not be enough. Then part B, a cell supplies a current of 1.2 amperes through 2 ohm resistor connected in parallel. When the resistors are connected in series, a current of 0.5 ampere is required. Calculate the EMF and internal resistance of the cell. And you could see this is simultaneous equation. Remember, we handled the simultaneous equation of the same kind. Now the interpretation is very important. We have the same cell. It's connected through 2 ohm resistor. Through 2 ohm resistor. Two ohm resistor connected in parallel. And then the current of 1.2 amperes is required from the same cell and internal resistance R. Now we are saying, when connected in series, the same cell connected in series with this resistance two ohm. This time round, a current of 0.4 amperes is required. Flows. So the question is, calculate the EMF and internal resistance of the cell. So we are going to handle case 1 and case 2, and then we formulate the simultaneous equations. So using E equal to I into R plus R. That is the formula relating the 3, where R is the external effective resistor. So in this case, we substitute for case 1. We are going to be having E equal to I, which is 1.2, into R. R here is the product of a sum. Product of the resistors over sum of the resistors. Plus the internal resistance R, which gives E equal to 1.2. 2 times 2 and 2 plus 2 are the same, which gives 1 plus R. So that is our equation 1. Similarly, for second case, this is case 1. E equal to I into R plus R. Substitute. E equal to 0.4 into R. Here the effective resistance will be 2 plus 2 plus R, which eventually gives E to be equal to, we can now say 0.4 into 4 plus R. So this is equation 2. So I have formulated the 2 equations. So our interest is to solve those 2 equations simultaneously. Have you covered simultaneous equation? Oh, then that's the life is now going to be very easy. So, which approach should we use? Elimination, substitution. Substitution. And substitution is obvious. If this is E and the other one is E, it implies this one is equal to the other. Isn't it? So let's try and see. So therefore, 1.2 into 1 plus r is equal to 0.4 into 4 plus r. So what is the easiest way of simplifying this one? What I can do to make easier simplification, we can divide by 4 by 0.4 on the other side. So 1.2 divided by 0.4 into 1 plus r equal to 4 plus r. 1.2 divided by 0.4, what do you get? 3. So we have 3 into 1 plus r, 4 plus r. So you can now collect like terms. When we open bracket here, we'll be having 3 plus 3r equal to 4 plus r. So if you collect like terms, take this 3 the other side and take r, bring r this side. We remain here with the 2r equal to 4 minus 3. Do you agree? Is it comfortable mathematics? Yeah? Yeah, I'm opening bracket 3 plus 3r, 4 plus r. Then here, collect like terms. Bring this r this side, become 3 minus r, which is 2r. Then we take this one the other side. So the 4 minus the 3 becomes that. So 4 minus 1 is 1, divide by 2, so r is 0.5 ohms. And then after getting r 0.5, can you now find fair to get it? Substitute in 1. In 1. So E is now going to be equal to 1.2 plus into 1 plus r, put r is 0.5. So 1.2 times 1.5, because this is 1.5. 1.4 times 1.5 gives 1.2 times 1.5. We give 1.8 volts. So therefore, the EMF, the internal resistance is 2, 0.5, and the EMF is 1.80. So opened, that one has been thoroughly done. Any questions as far as that one is concerned? Members, we need to always ask good questions. Someone who sent me a message on WhatsApp, "Teacher, I am not understanding current electricity." Then I said, from where? From the beginning. Now, how could we answer? We began from electric cells. We had, I think, there are around 3 lessons that has moved. 4 lessons. Now, how can I now relate from the beginning up to where we are? So I advise you people of the same category, read it through. Or if there is any challenge, send your queries instantly before we go ahead. Otherwise, you are going to be finding serious challenges. So when you are getting response, get a response that will help me also help you. Is that one okay? Okay, this if there is any response to tell you. Number 3, define the term internal resistance of a cell. I think that one is what I began with here. Wait, anyone, do you recall internal resistance, how we defined it?
is the opposition
Mm.
to the flow of current because of chemical composition.
Yes, is the opposition to the flow of current within the cell due to its chemical composition. In other words, the opposition is offered by the chemicals within the cell. They resist current flow through them. So that is what we call internal resistance. But there is also a second definition that we gave, although I didn't emphasize it because some people were not interpreting it very well. I say it is the effective resistance in series with the external circuit that accounts for the loss of energy within the cell. I think that one is too long. But even the first one can do. The last question, was it the last question under activity 1? Yes. A cell of 1.5 volts and internal resistance R is connected in series with 5 ohm resistor as shown below. Do you see the diagram? Here. 1.5 internal resistance is not given. 1. And the external resistor was 5 ohms. So the question is, if the current in the circuit is 0.25 ampere, find R. How I wish someone can help me find R here. It looks to be straightforward. You want to come? Yeah, people can see you bring your clear presentation here. Which formula should we use? E is equal to I into R plus R. The EMF is 1.5, I is 0.25, R is 5, internal resistance is small r. It is that one was too easy for us. Alright, answer is? What is the answer? You can divide both sides by 0.25. Remain with 5 plus R. 0.25 is what? 6. 5 plus R. Therefore, R is equal to what? 1 ohm. R is equal to 1 ohm.
Question.
Yes.
Notice is asking, can't I align the numbers in the middle of the cell?
Can I what?
Align the numbers in the middle of the cell.
Someone is asking a question, I've not interpreted it very well. He's saying, can't I align the numbers in the middle of the cell? Where? Here?
Inside
The cells. Like
Inside.
5 ohm, we put them inside.
Inside?
That
is not a cell. This is a resistor. Inside, this is what we call a cell. Putting the number, it doesn't matter wherever you put it, as long as we make the same interpretation. Okay, I think activity 1 is done. The experiments we did. Now we go to activity 2. Activity 2 was a solid activity that requires people who had time to interpret the question. Unfortunately, some of you just relax as you go home. Okay? So, we had 6 cells. Activity 2. We had 6 cells. 1, 2, 3, 4, 5, 6 cells. And each of these cells was of EMF 1.5. We had a current diameter of a resistor, and we also had a lamp. Something like that. This was the filament lamp. So the question was saying, the ammeter reading was 3 amperes. 3 amperes. And the voltmeter reading was not given, so we need to find it. And the resistance was 1.4 ohms. The resistance was 1.4 ohms. The internal resistance of the cell was 0.1, and the EMF of each cell was 2 volts. Now, interpretation comes our way. So we are looking for the PD. We are looking for the PD across the lamp. The PD across the lamp. How are we going to do that? For those who try. How I wish some people post some answers here and they see whether they did the work or not. Here, we are having 6 cells, each of EMF 2 volts. That means the total number of volts, total EMF E is going to be 6 times what each of the EMF gives. So we give 12 volts. We get 12 volts. And internal resistance, effective internal resistance. Effective internal resistance is going to be the internal resistance of one cell times the number of cells, which is going to be 6 times 0.1. Much as I'm using times, the reality is it's supposed to be adding 0.1 plus 0.1 plus 0.16 times, and then we get the effective internal resistance to be 0.6 ohms. Because they are in series, if they were in parallel, it would be a different case. Now, we have 2 approaches. I wonder which one is going to be convenient for you. I get you. We have 2 approaches. Now it implies that the supply EMF is 12 volts. The current is passing through 1.4, meaning that you can get the PD across R. You can get PD across R. PD across R, I'll call it V1, is going to be equal to IR. Call it IR1, which is now going to be equal to the current, which is 3, times the resistance, which is 1.4. And that PD will get it to be 4.2 volts. That's the PD across only R. But remember, there is PD across R, there is also PD across the lamp, and there is also PD required to overcome the internal resistance of the cell. Are you getting it? So, what can we do? The question is asking to get the PD across what? The lamp. So what we can do, let's first get the terminal PD. You know what you call terminal PD? PD across R and PD across. When you add the PD here and the PD here, you get the total terminal PD. So what we can do, let's get the terminal PD first. Terminal PD V is now going to be equal to the EMF of the cell times PD required to overcome the internal resistance of the cell. When you see the expression is like this, E is equal to V plus IR. You can say E is equal to IR plus IR. So I into R plus R. So we're saying our interest is this one, terminal PD. You get this one, subtract of the one for the internal resistance, so you get the answer to be the EMF, which is 12, minus current is 3, the internal resistance is 0.6, so 12 minus 3 times 0.6 gives what? Gives 1. What? 1.8 minus 12, 12 minus 1.8, you get 10 volts. So, that means terminal PD is 10.2. Terminal PD involves PD across R and PD across the lamp. That means if we already know the PD across R, we can now get the PD across the lamp. Is that one okay? So then therefore, PD across the lamp, I'll call it V2. PD across the lamp is going to be for the whole terminal PD minus PD across R, 4.2. And that one gives the PD to be 6.0 volts. That's then the PD across the lamp. And now for resistance of the lamp, this is now Roman 1. Resistance of the lamp from Ohm's law. Resistance R is equal to V over I. The voltage across the lamp, which I call V2, is going to be 6, and the current across the lamp, since it is in series, the current is the same. That means resistance of the lamp is 2 ohms. Resistance of the lamp is just 2 ohms. That is one approach which I don't know whether it is comfortable with you. This approach was finding the terminal PD. Are you getting it? After getting terminal PD, you subtract off the PD across R. The remainder will be the PD across the lamp, which some people may not approve. Okay, let's use the second approach. Alternatively, we can use E is equal to I into R plus what? R. But you need to know that this capital R is the PD across the lamp and PD across the resistor. Are you getting it? Where R is the external resistor, where R is the external resistor, and if R is the external resistor, therefore R is equal to the resistance here of 1.4 plus the resistance of the lamp which you are looking for. That one now agreed. So now, if we substitute in a formula, I think this approach is much more easier. No, not the second one is much more easier. So now we substitute here. EMF E is 12. I current is 3. R is 1.4 plus R prime, which we are looking for. Internal resistance is 0.6. So we're only looking for R prime, isn't it? So for R prime is equal to, just divide by 3, 12 by 3, you get 4. 4 minus 0.6, get 3.4. Subtract off 1.4, you get R will be equal to 2. Okay, I'll just use the shortcut. Subtraction mathematics. Because any other step you carry does not qualify in a mark. I get it. So someone can just use mental work here. This one divided by 3, you get 4. 4 minus 0.6, you get 3.4. 3.4 minus 1.4, you get 2. I think it does not need to calculate. You get the answer. Then after getting what R represents, then you can say PD across the lamp. From Ohm's law, which I call V2. Is equal to IR, I is 3, R is 2. So the PD is 6 volts. Either we are getting the same answers. Here we have got the answer for Roman 2, Roman 1, and this one is the answer for Roman 2. Here we go Roman 2 first. Now, which of the approaches is convenient to you? The first, the second. That's someone they say the first is much more easy. The second. Eh?
You can just confuse it.
Wait.
Because you have to go back and let's see then look for the I.
And in the second, we first found the R. And then use it to find Roman 1. Here, in this case, for us here, we first found PD across R1, we subtract it from the other side. Here, you need to be very intelligent here to know what you are doing. And then here. Is that one okay? Alright. Then the question is numbers. So that was activity 2, number 1. Activity 2, number 2 is also having some degree of intelligence which you need to apply. Do you see the circuit? Numbers. Do you see the circuit? Yes. The question 2. Unfortunately, we have not even done what we are supposed to do today. We are reviewing what happened in the other day. We had the resistors like this connected in parallel. They are connected in parallel. We had an ammeter somewhere, and we had another resistor. Then we had the cells also arranged in this manner. and then back to the source. Two ohms, 1.5 volts, 0.2 ohms, then 1.5 volts, 0.2 ohms, 0.57. Into a 1 watt. Okay, that's how the circuit works. We have to find the ammeter reading when current flows. We have to find the ammeter reading when current flows. Is the circuit so scary? Is it so scary? Don't worry. So what is the question asking? Ammeter reading. In other words, they want the current flowing in the whole circuit. Now, if you want the current flowing in the whole circuit, then what you are going to do, you are going to first of all do the effective EMF. What do you think is the effective EMF? Effective EMF P is going to be equal to what? Yeah? Not 3. Is it 1.5 or 3? Because I can see 1.5 here and 1.5 here. Yeah? What are you suggesting? 1.5. Why?
Because they are the same as the
Yes, because they are connected in parallel. The effective EMF is the EMF of one cell. The EMF of one cell since their ends are joined. So the PD across one cell is the same PD across two cells, same PD across three cells. How about effective internal resistance? Effective R is going to be equal to what? Effective internal resistance. So the effective internal resistance is not what? No, the effective internal resistance is going to be product of a sum. So the resistors, once they're in series, and there are two resistors, product of what? Sum. So the effective resistance is now going to be 0.1. Yeah?
Yes.
Pardon? Hey, thanks. So therefore, now we want effective resistance in the parallel setting. So these resistors that are in parallel, we also need to get them. Are you getting it? So effective resistance in the parallel setting. In the parallel setting, this is going to be equal to what? We call it R parallel or R prime. Since they are in parallel and they are more than one, so you're not going to use product of the sum. We're just going to say 1 over R is equal to 1 over the first resistor, which was 1, plus 1 over 1, plus 1 over 1. Which answer equal to what? 3. 3 over 1. So therefore, R prime is going to be 1 over 3, which is the same as 0.3 ohms. That is in the parallel setting. Now we know, after getting the internal resistance, now we are going to now sum up effective resistance in the external circuit. Effective resistance in the external circuit that is external circuit, meaning that the resistance, this is the internal circuit, internal resistance. I'm talking about this one and the other one. So we are going to add this one plus this one plus this one. These are the external. Here the same is internal. So that's now going to be 0.3 plus 0.57 plus 2. So total gives 2 point what? Are you sure? It gives 2.9. It gives 2.9 ohms. So now our interest. Now from all along what we wanted is to get all values that can be help us to use this expression. I get me. Because by now we have internal resistance R, we have capital R. Because capital R is the external resistor, including the one in parallel, this one and this one. So the EMF, we already have it. We say it's 1.5. So we substitute in. This is now going to be 1.5 equal to current I is what we are looking for. External resistance 2.9, internal resistance 0.1. So we can now get I. So therefore I is going to be equal to 1.5 divided by 3. Because 2.9 plus 1 is 3. And that one gives 0.5. So ammeter reading is 0.5 amperes. The ammeter reading is 0.5 amperes. But have you found serious challenges in the number? You think you are just scared by the body of the diagram, but when you realize all along we are wanting to handle something as easy as this. Alright, now we go to what the intention of our lesson today was. The exercises were too many, so that is the reason why I am filing. Okay. Alright, we go to electrical power and energy. Electrical power and what? And energy is our area of concern today, which we want to exploit within the few available minutes left. Alright. Now, suppose we have a potential difference V maintaining a steady current I in a circuit at time t. Charge that flows Q is equal to IT. You remember, quantity of charge is given by IT. Then work done to move that charge is given by QV. The work done will be given by what? QV. Charge times potential. Because remember how we are defining potential or PD. PD is the work done. You know PD is the work done. To move one column of charge, if Q is 1, I get it. It implies that V is equal to work done. I get it. So PD, V, is the work done to move one column of charge from one point to another in a circuit. Are you getting it? From one point to another in what? So therefore, what done is QV, if Q is any other charge times the PD. So now, if we substitute where there is Q and we replace it by IT, therefore the work done is now going to be equal to ITV. And you see, electrical work done, usually when current passes through any given conductor, there is work done in converting the electrical energy into heat and heat or light energy. Are you getting it? In other words, work done is energy. Work done is what? Energy. Because it is converting from one form of energy to another. That is from electrical energy to heat energy and then light energy if it is a bulb, or sound energy if it is a radio and so on. And therefore, we are concluding by saying that therefore, electrical energy equal to IVT or ITV. ITV. Or we can write it as VIT. So the electrical energy is therefore given as VIT. But you can have other expressions. You can replace from Ohm's law, V is equal to IR. Where there is V, you can replace it by IR. And then turns out to be I, which is I, and this I becomes I squared or T. So that means electrical energy could also be phrased as I squared or T. Better still, you can substitute for I in Ohm's law. Can't you substitute for I? Or you substitute for I, what do you do? Still, from Ohm's law, I is equal to V over R. So if we get electrical energy, electrical what? Energy. And where there is I, we substitute by what? V over I. We remain with V times another V, which becomes V squared over R times T. So electrical energy could be given as V squared over R, could be given as I squared RT, could be given as VIT. So these are the three expressions for electrical energy. Having got those three expressions for electrical energy, we can go ahead to get electrical power. You know, power and energy is almost the same thing. All the other one is just time factor. Remember, how can we define electric power? Electric power. Electric power. If in your ordinary physics you define power as rate of doing work, and you have noted that here energy is the same as work, what do you think electrical power is? Just a short statement. Eh, Yes, therefore electrical power is the rate at which electrical energy is dissipated. Electrical power is the rate at which electrical energy is dissipated or consumed in a circuit. You see, there are two things. There is dissipation and also consuming. Dissipation is given away. In other words, so it is dissipated in form of heat, or dissipated by converting it to other forms of what? Energy. Or consumed or utilized by the conductor itself. Are you getting me? So, we can define electrical power as the rate at which electrical energy is dissipated or consumed in a circuit. Rate at which electrical energy is dissipated or consumed in a circuit is called what? Electrical power. Or you can say it is the electrical energy liberated in a conductor per second. Are you getting me? Electrical energy power per second is also power. And that's why we are saying electrical power is equal to electrical energy over time. Over time. The rate is simply the rate or electrical energy passed per unity time, per second for that matter. Is that one okay? Rate means per time. Are you getting me? Of electrical energy consumed in a what? In a circuit or in a given conductor. Therefore, power P could have also three expressions. When we decide to use this, let's see what is happening here. When we decide to use E over T, here this is going to be VIT is going to be equal to VIT over T. That gives VI or IV. When we decide to use still E over T, but this time around we're using I squared RT. The electrical power becomes I squared R. When we decide to use the P equal to V squared over R, V squared over R, T. Because everything here is divided by T. You realize that we are getting V squared over R. Therefore, expressions for power are three. This one, IV, I squared R, V squared over R. Those are the three expressions for power. So when we come to calculation, when we calculate for power, you look at for either, do I have V or I? Do I have I or an R? Do I have V or an R? Whatever you have is what you use. SI unit of work is the watt. My teacher used to ask, what is a watt? Yes, a watt is a watt. The unit of power, and is given by, is the rate of working of 1 joule per second. You getting it? The watt is the rate of working of 1 joule per second. Rate of working of 1 joule per second is what we call the watt, because 1 watt is 1 joule per second. 1 joule per second. You can see my friend is getting exhausted. I'm about to wind up, don't worry. Because the topic here is short. Other units of power, we may have kilo, watts, and you may have megawatts. You can also have milliwatts. But the common ones are kilowatts and megawatts. You normally hear the president say, we no longer call it on falls down. We call it what? Tira. Tira Dam is producing 400 megawatts. In other words, we are talking about the power we can generate. Negative it is usually we are dealing in megawatts. Mega means a million watts. Negative or 1,000 kilowatts. Okay, some questions here. Examples. When you go to examples, you just know you're winding up. Example 1. A current of 12 amperes passing through a resistor of 3 ohms. Calculate the PD across the resistor and the power used by the resistor. Do you find any challenge in such a number? Or you are going to say usually teachers give the easiest number at the start and leave us with the complicated numbers. Pardon? We give the easiest number as example. And the reason why we do it that way is because we need to begin from, if I begin with a difficult number, then you may lose hope. So now see that the thing is possible and then you can continue. The next thing, teachers, all numbers are easy because it does not distinguish between the difficult one and the easiest. Okay, now we have current I is given by 2 amperes. And we are given a resistor of 3. And what else? Find the power, PD. PD, how will we get PD? No, I think we can do the easiest. What is PD? PD is equal to what? Does it need thinking? Yeah? IR. I is 2, R is 3, answer is 6 volts. That one is done. Another one, power. How can we get power? Power is given by what? Electrical power. Which of the things? I know ladies are mostly, they enjoy IV most. IV is very easy to remember. So IV, the I is 2, the voltage is 6, the PD is 12. The power is 12 watts. Now you realize here, any of those formulas could give you the same answer. Are you getting me? If you decide to use I squared R, just get 6 squared is 36. So 2 squared is what? 4 times R. Right? The answer is the same. So whatever you decide to do. That is question 1. Question 2. Question 2. A lamp is rated. This one you need to think. There, it is you see, we are giving easy examples. This one is a hard example. A lamp is rated 240 volts, 60 watts. What does the statement mean? On your lamp, usually the bulbs you have at home, I indicated 240 volts, 60 watts. What does that one mean if you see it on the bulb? Mm-hmm. Mm-hmm. Yes, that is exactly the thing. But whenever you connect this appliance, this lamp, to 240 volts, the power it will give you is going to be 60 watts. That's simply what it means. So you can say when the lamp is connected to 200-volt supply, it delivers a power of 60 watts to convert electrical energy to other forms of energy. Are you getting it? If now it is the bulb, it is going to make light energy. In other words, maybe we are saying that if it is connected to we are saying when the lamp is connected to 40 volt, it means when the lamp is connected to a 240 volt supply, it delivers, means gives out a power of 60 watts to convert electrical energy to light energy. So that is what the meaning of the current. Alright, now a question, Roman part B. Find the current consumed by the lamp. How can you get the current? If you have volts and power, can you get the current? What expression should we use? So power is equal to what? IV. Therefore, we want to get current. Therefore, I is equal to power over volts. The electrical power was given according to the question 60 or 240. So implying that current I 6 over 240 gives what? Yes, a quarter, isn't it? So 0.25 amperes. Then that is B Roman 1. Roman 2. Resistance of the filament. Resistance of the filament. Which formula should we use for power? Eh? Which formula? We have three. IV. I cannot find R. We are looking for resistance of the filament. We need to look for expression for power that has resistance. We can use I squared R. So remember, we are looking for resistance. So the power is 60 watts. Current is 0.25. So we can find R. And that one gives R to be what answer do we get? We can get 960 ohms. Or you can also use the other formula. You can use Ohm's law. You can also use Ohm's law. R is equal to V over I. Isn't it? And then V is 240. The current is 0.25. And still get the same answer. You get the same answer? When you press the calculators. So I think we are through with the examples. Okay, there is a third example. Third example before we end with the activity. Third example. immediately. Right. So I had a battery of EMF of 24 volts. 24 volts. And then resistance R of that. We had a lamp here, which is indicated 10 volts, 20 watts. Lamp. It's an incredible lamp. It uses 10 volts and produces 20 watts. Yeah? So if the bulb is operating normally, find the PD across the resistor. Members, how can we get the PD across the resistor? The supply voltage is 24. This one consumes 10. What does this one consume? Yes. Okay. Okay. Across R. It's going to be called what? Yes? What? This one does not require formula. It's just common sense. Yeah? You have a supply of 20. Now this one is consuming 10. What will this one take? Yeah? Yeah, we have been very dependable today, so focusing more on you today. Young man, what is the answer? It is going to be simple 24 minus 10. So this gives 14 volts. We have answered one on one. Very easy. What is 14 volts? The PD across the resistor is what? 14 volts. Then the value of R. The value of R. Now, you cannot find the value of R before you find the current across R. Are you getting it? So you need to get the current across R. But since the resistor here is in series with the lamp, it implies that the current across the lamp is the same current across R. So let's find current across the lamp. We have found the current across R. So from here, how can we get current? Is it correct? Have you forgotten? IV. Yes? Yes? Power is IV, therefore I is power over V. So the power is 20 and the voltage is 10. Therefore the current is 2 amperes. After getting the current, you cannot use Ohm's law. Already we have the PD across here. So you know the current, you can find the resistance. Now therefore, R here is from Ohm's law is equal to V over I. V is equal to IR. That means R is equal to V over I. And that the V across the is 14 already. And then the I is 2. So resistance of the lamp is 7 ohms. I think you are realizing things are not all that complicated. The only problem we are having with this is that you're not practicing. If you're not practicing, every simple thing becomes a complex thing. But you give yourself time, and then you practice. You're going to find this current electricity very easy. But if you are just keeping the notes, thinking that you're going to read it like the way you see how the money migrated from their pedal, then it's going to be very difficult this time round. Everything. Lastly, power dissipated in R in the resistor. Power dissipated is going to be equal to I squared R. We know current is 2, and the resistance we have it is 7. And the answer is 2 squared times 7 is 1. Thank you so much. So we are through with all the examples. Now it is your time. It is your time. There is an activity that you are going to do. This activity is having only 2 questions. And they are circuit diagrams. They need thinking. And the reason why I give them to you in advance is to think about them and then find them. But you note, have you noted? We have indicated activity 1, meaning that the lesson continues with something little we want to talk about. Right through, we continue. I want to end with this thing. That exercise you will do, it's called activity 1. We want to do something little called energy costs. Energy costs. Energy costs. So, among the biggest utilities in our home is power, isn't it? And the cost of utilities at home that consumes the largest fraction is, you call it what? You call it Yaka. Yaka is the highest consumption in terms of utilities. And therefore, we need to know how to calculate these costs so that it helps us in 2 ways. 1, to minimize expenditures on gadgets, on electrical power, and 2, not to be cheated if we are able to verify how these calculations are brought about. Meaning that you need to know the cost of 1 unit of electricity. I don't know what is the current unit cost? Someone will say, as long as I'm not paying, I don't want to know. What is the current unit cost? What does the unit cost? 200. Then we'll be celebrating in Uganda. Someone is saying it is around 200. 250. Then we'll be celebrating. We'll be celebrating. The unit, by that I also don't know the exact, but I know it is around 800 to 900. Between 800 to 900. Around there. The current unit. But of course, these people are cheats. The service, they pay for what they call service fee. Even if they have not done any service to it, they deduct. So sometimes we may not be able to know the exact amount consumed. Now, what I was saying, we are saying electricity boards like women charge for the energy they supply. Are you getting it? And the unit of electrical energy is what we call a kilowatt hour. Is what we call what? Have you ever seen this symbol? Okay. Have you ever seen it anywhere? This one. Yeah? Have you ever bothered to know what it implies? Yeah? That's what we call a kilowatt hour, is what we call a unit of electricity. 1 unit of electricity is what we call what? A kilowatt hour. And therefore, what is a kilowatt hour? A kilowatt hour is the electrical energy used by the appliance at a rate of working of 1 kilowatt in 1 hour. Are you getting it? In other words, whenever you use your appliance that is indicating 1,000 watts, and use it in 1 hour, then what the electrical energy used is what we call a kilowatt hour. Kilowatt what? Electrical energy used at a rate of working of 1 kilowatt in 1 hour. Are you getting it? At the rate of working of 1 kilowatt in 1 hour. So electrical cost. Therefore, how do we calculate electrical cost? The formula is very simple. Get power consumed in kilowatts, multiply by the number of hours used, times the cost of 1 unit. Then you get the total cost. Are you realizing, is it a very difficult formula? Yeah? So we're saying electrical cost. Electrical what? Cost is equal to power in kilowatts. Power in what? In kilowatts. Times time in hours. What? Times cost per unit. Cost per what? Per unit. Per unit. So the formula is PTC. Isn't it a very good formula? What is it? Cost. Electrical cost. Is equal to power in kilowatts, time in hours, and then cost per unit. Example. Find the cost of running 5 60 watts lamps and 4 100 watts lamps for 8 hours if electrical energy costs 500 per unit. Now, need a serious interpretation. Are you getting what I'm saying? I'm saying, find the cost of running 5 60 watt lamps. Are you getting it? And 4 100 lamps. And you're using the time of what? 8 hours. 8 hours. So how could we handle this? So we need to get the total power. Are you getting it? We need to get what? Total power. Total power. We are going to be having 5 times 60 plus 4 times 100. So the total power now going to be 5 times 6 is 40. This is 300 plus 400. So that you get 700 watts. Isn't it? So now we have now got the rest is now okay. We can now substitute. I think this is one of the easiest current electricity because there are no formula there interchanging the things, just calculating our money. So we want electrical cost. Electrical what? Cost. We said it's given by a PTC. But the power is in kilowatts. So we get the power in kilowatts. So we get the 700, we convert it to kilowatts. Really? Then the time in hours will be given 8 hours. And then the cost per unit is given as what? 500. So we can now simplify. What answer do you get? 70 times 8 times 5. Actually, 70 times 8 times 5 is 40. 4 times 7 is what? 28. So how many zeros do you have? Yeah? You have 2 zeros. 1 zero. Huh? So the answer is 280. Is it in shillings in what amount? Okay, in this amount. So that is the amount we have to pay if that is our consumption rate. That is example 1. 2. The example reads, a house has one 100 watts lamp, 275 watts bulbs, and 5 40 watts bulbs. Find the cost of having all lamps switched on for 2 hours every day for 30 days at a cost of 300 per unit. It's definitely becoming too mathematical. Yeah? So, can we get total power consumed? Yeah? Total power. So total power, we have 100, and what else? 275, and 4 times 40. So the total power is what? This is 150 plus 160. Yeah? You get what? 140, 160. Yeah? 410. So that is very easy. Now what is? Time is what?
2 hours
Very easy. Therefore, electrical cost is going to be equal to PTC. The power is 410 kilowatts. The time is what? 2 hours. But it is for 30 days. Yes. 30 times cost per unit. What is the cost per unit? 300. So now what are we paying? So we pay what? Is that on 410? 450. There were, according to the question, we have 5 40 watts bulbs. We had 5 G. We had 5. So this is now 20. 200. 200 plus 350. 450. What are you doing to me? I say, with mathematics teacher is this way. Who cannot add very well? So the final answer is what? That is? Yeah, the answer is 8,000. I don't think it's just a lot. Yes. Yeah? Okay. So final answer is students 800 what? 8,100. Do you need another example? No, you're becoming too easy. Okay. If that is the case, Then there is activity 2. I think that's where I'm going to end. Activity 2 is having only 5 questions. Having only what? And I've attached answers. I've attached what? Answers. So I want you to practice them. By the time we come next time, we'll be through with the answers. How I wish you can also send me the answers on WhatsApp and I'll see what you do. I gave out the number very many times. I can even repeat it to confirm whether we are doing the right thing. That is the number. So if you are free, you can now send me the answers, then I'll verify the fact. By the time I come here, I'll be now knowing people who are following and those who are not following. Okay, thank you so much for your patience, commitment in sharing knowledge with us. I wish you the best of the day.